Welcome everyone to the first lecture of Lecture 3, or the first part of Lecture 3. We're going to talk about kinetic factors. So one of the things, the overarching thing that we are going to be talking about in all of the parts of Lecture 3 are reaction rates. Now reactions occur at several different rates, anywhere from very fast, like an explosion, that's a very fast rate, to something that is very slow. For example, rusting. Actually, explosions and rusting are the same type of reaction. It's just a matter of how fast they occur. Wouldn't it be terrible if rusting was a fast reaction? You'd be driving down the road, you'd hit a puddle in your car would get wet, the metal would start to rust, boom, there goes your car. Thankfully, that's a slow oxidation reaction, whereas an explosion is a very fast oxidation reaction. So, fast rates, slow rates. We want to talk about what controls that rate of reaction. So the rate of reaction is controlled by three primary factors. We have concentration, we have temperature, and we have structure and orientation. We're going to talk about each one of those in detail here. So let's look at concentration first. Now there's a theory that goes through about how reactions occur called collision theory. And this basically says that reactions require collisions to occur. Reactions don't just happen when molecules pass by one another. If there's space and no collision happens, then you're not going to have a reaction. So the reason we require collisions to occur is that bonds have to be broken and bonds have to be formed. We use the energy of a collision to break a bond, and then we use the proximity of atoms to each other as they collide to form bonds. So we always have to have these collisions. Now, as far as concentration goes, the higher the concentration is, the more collisions you're going to have. Imagine that you're in a room walking around. If there's only 3 of you in that room, you'll bump into each other once in a while, but not very frequently. But what if there's 30 of you in the exact same room? You're going to run into people a lot more often. You're going to have more collisions, probably some more reaction depending on how hard the collision is. But the higher the concentration, the more collisions there are. The more collisions there are, the faster the reaction rate will be. And vice versa. The lower the concentration is, the fewer collisions you'll have, and the slower the rate will be. Let's turn our attention to temperature. Again, we said that collisions are needed to break and form bonds. Well, what does temperature have to do with collisions? A lot, actually. Mainly because temperature affects kinetic energy. Temperature is nothing more than a measure of kinetic energy. So the higher the temperature, the faster things must move. And the faster things move, the more likely they are to collide, and the more likely they are to break or form a bond. Go back to your little mental model here of people in a room. If there's 3 of you walking in a room, you might collide once in a while. If you're all running in a room, you're going to collide more often, and you're more likely to break something. Okay, so the faster you're moving, the more you're going to collide, and the more likely that the collision will have enough energy to break or form a bond. Now, as temperature increases, the reaction rate will increase, and vice versa. As temperature goes down, reaction rate will go down. The last thing I want to talk about, it's a little strange, you may not have ever thought of this before, but that's the orientation of a collision. Now, what does that mean? Well, orientation refers to the relative position in space of the molecules during a collision. How are they positioned to each other? There are a lot of reactions that have collisions that need a very specific orientation in order to break or form the specific bonds that you want for a particular reaction. So the end result is that you may have lots of collisions, but lots of collisions may not result in a reaction. Not every collision will cause a reaction, so as a result you have a lot of ineffective collisions. Let's look at how that might work graphically here. So if you have a reaction that has collisions with a very high orientation requirement, that means that you're not going to have all of your collisions resulting in a reaction. So let's see what that looks like. If you have a high orientation requirement, that means that your collision must occur in a very certain place in order to break or form the proper bonds. Now, in this reaction here, what we see is we've got a fluoride ion here. It must collide with this carbon atom here in order to break this carbon-chlorine bond and form a new bond between the carbon and the fluorine and kick this chloride ion off of that molecule. Okay, so what happens is this has to come in right in there between the hydrogen atoms. If it collides here, here, comes in here, goes in there, none of those will result in a reaction. It is a collision, but it's not a collision that will break that carbon-chlorine bond and will not result in the reaction that you want to have happen. So most collisions occur without proper orientation. So every reaction has several collisions that happen, but most of those collisions do not have the proper orientation and do not create a reaction. So all of this falls under the branch of kinetics. Basically, kinetics studies the rate at which a chemical process happens. Besides information about how fast a reaction is going to go, we also start looking at things like a reaction mechanism, how that reaction occurs. And we'll talk about reaction mechanisms a little bit later in the lecture.